Good day, madam. I'm Dineshwari Tanasakran, and I'm going to uh, present about the RC high pass filter, and my friend Sarah will be presenting about the RL high pass filter. Okay, so here is my calculation for TF, and before that, after completing this experiment, we are expected to determine the transfer function and cutoff frequency for a high pass filter circuit, and also we are also expected to determine the frequency response for high pass filter circuit by using the straight line approximations of the Bott plot, and also to compare the actual frequency response and the approximations of frequency response for a high pass filter circuit. Okay, so here is the TF, and I've calculated the TF using the formulas even, also for the omega C and also the frequency. So here are my calculations. I got a 6.447K for TF, and omega C I also got 6.447 kilohertz, while for frequency, when we converted it into frequency from omega, we got 1.026 kilohertz. The purpose of us converting the value of omega C to frequency is to ease us when drawing the Bott plot, because the units in Bott plot are given in kilohertz. Okay. Sorry, it is given in the form of frequency, not omega C. Okay. So a little bit about this RC, about the high pass filter. High pass filter actually permits high frequencies to pass from the input through the to the output of the filter. Okay, so as in the low pass filter, the cutoff frequency FC is the frequency at which the amplitude of the output voltage is 0.07 of the maximum amplitude. But in the high pass filter, the maximum amplitude occurs for higher frequencies rather than for lower frequencies. Okay, and since the frequency corresponds to the half power, the cutoff frequency is also called the half power or 3 dB down frequency. Okay. Other than that, this high pass filter, I found out that it attenuates the low frequency components. And in high pass filter, higher frequencies are preserved compared to low pass filter, where lower frequencies are preserved in low pass filter. Okay, so in terms of circuit construction, in low pass filter, the resistor comes first and then we can see the capacitor. But in high pass filter, the capacitor comes first and then followed by the resistor. Okay, so for the circuit construction, we have assembled a circuit just like in figure 2, and we have connected the oscilloscope's channel 1 to the input voltage, and the amplitude has been adjusted at Vin around 2 Vp or 4 Vpp at a frequency of 100 Hz, and the frequency will be adjusted until 10 kilohertz to find out the V out. Okay, so from there we have determined the cutoff frequency, and the cutoff frequency we got is 850 Hz. Okay, so moving on to the results. For the results, as the frequency increases, all three elements also increases, which is V out, voltage gain, and voltage gain dB. All these three elements also increases. But if compared to low pass filter, for low pass filter, as the frequency increases, the V out decreases, and also the voltage gain in dB decreases. So as for high pass filter, all these things are increasing. So this is the results that we got. This is the graph that we are able to sketch, the dot plot. Okay, so for 10 hertz, 10 kilohertz, we got 0.004, but we have taken it to the nearest. Approximately we took only 0 dB for 10 kilohertz. Okay, so here is what we got. Okay, so going on to the circuit construction, I've got to mention this earlier. Okay, so for the circuit construction, I've made some try and errors, and I found out that for multisim we not only can use a function generator, but we can also use the voltage source, I mean AC voltage source, straight away by adjusting the VRMS. Okay, so let's say we take 2 VP, we convert it into VRMS, and use it we can use that VRMS and adjust the frequencies as the following, like this, and we are able to get the same results. So there are two ways of constructing the circuit. One is by using the function generator, or we can straight away use the AC voltage source. Okay, so thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nasaruschi, and then I will present to you my part. That is part 2, RL high pass filter. Okay, so as you can see, what we have done here. First thing first, we have done the pre-lab. So based on this circuit, we have calculated the omega C and the FC. So this is the calculation that we have pasted here. Okay, so for the circuit construction, based on the circuit, we have done the lab as well through multisim, and then given the frequencies like from 100 Hertz to 10 kilohertz, we have to find out the V out, the AV, and the AVDB. So today I will show you how to measure the V out from the multisim. Okay, so so as you can see here, I've run the circuit. So in this multisim, we use the oscilloscope function generator, a resistor, and inductor. So this is the connections that we have connected to provide to jot down the results. Okay, so I will demonstrate you on how do we get the data for the V out. Okay, first thing first, I will try 400 Hertz with the 2 VP, because it was stated in the circuit that the V in is 2 volt. After that, okay, and then so first thing first. Okay, let's put it in random. Because I will do it one by one. Okay, here. Okay, to achieve the V out, you need to measure only the channel B, because we have connected the channel B to the inductor. Okay, so first we select a trace at channel B. Okay, and we set the value to Y max, go to the next Y max. Okay, and then we read the reading at the T2 channel B. T2 channel B, because because I'm using the T2 cursor, so let's read it at the T2 channel B. So it's at 202.111 millivolt. So this is the V out that we got from this oscilloscope. So let's try another value. Let's try like around 1 kilohertz. Oops, 1 kilohertz. Okay, 1 kilohertz. Okay, so so we can adjust the time scale to what your eye feels comfortable to view the circuit. Okay, so I'll adjust it like right here. Okay, so you can also adjust the the scale. If you adjust the scale, if you're adjusting the scale, it would not affect the result. So yeah, so use whichever cursor that you like, 1 or 2, and then just press right click and go to the next Y max, and tada, you'll get the result right here. So let's read it at the channel B, the pink one, and T2, because I'm using the T2 cursor. So the result is 491.896 millivolt. Okay, so yep, that's the two examples on how to read the V out using multisim. Okay, so next, oops, okay, so now using the V out, so we calculate the V out divide by V in, 2 volt. So this is the result, and from there we use the calculator to enter this formula, and we got this result in mostly negative except for 0.15. So we've plotted the graph, the AV dB versus frequency, the dot plot. Okay, so the discussion. So explain the differences between low pass and high pass filter circuits. So the low pass filter attenuates the high frequency, while the high pass filter attenuates the low frequency components. The low frequency is preserved in the low pass filter, while high frequency is preserved in the high pass filter. In terms of the circuit construction, low pass filter consists of resistor that is followed by a capacitor, whereas the high pass filter consists of capacitor that is followed by a resistor. So the example of band pass filter, low pass filter, and high pass filter circuit application in our technologies today. The band pass filter are widely used in the wireless transmitters and the receivers, such as the RFID system at the tolls nowadays. And while the high pass filter are used in the speakers for amplification purposes. Low pass filter exists in many forms, including the electronic circuits such as the His filter used in the audio, and aliasing filters for conditioning signals prior to analog to digital conversions, digital filter for smoothing sets of data, acoustic barriers, blurring of images, and so on. So from this lab, we have concluded that the high pass filter has a gain response with a frequency range from omega to infinity, and inputs having a frequency below the cutoff frequency, omega, gets attenuated or rejected. Anything above the omega passes through the unaffected. So that's all from me. Thank you.